This is problem set number 6, problem 4. A kitchen floor which is 3 meters long by 4 meters wide has a charge Q naught which is equal to -2 microcoulombs, spread uniformly over the whole area. A point charge Q1, which is equal to -5 microcoulombs, is suspended a distance of 10 centimeters or 0.1 meters above the floor, near the middle of the room. Part A, what is the electric force that acts on the point charge? Derive any formulas used and don't use pre-derived textbook equations to plug and chug. There's a hint to use Gauss's law and take advantage of the fact that the floor is very long and wide compared to the distance to the point charge. So we have an infinite sheet, right, essentially. Okay, so I drew a diagram here of our kitchen floor. It has a width of 4 meters and it has a length of 3 meters, right? And this whole kitchen floor right here has a uniform charge of 2 times 10 to the -6 coulombs, okay? All right. So in order to find the electric force of the point charge, I'm going to use the formula for electric force. So that's F, that's the electric force, is equal to point charge Q times electric field E, right? So that's a formula we should know. So that's the electric force. That's a point charge. And that is the electric field. Okay. So I'm gonna use Gauss's law to solve for my electric field first, because I already know the point charge Q, that's -5 microcoulombs. So since I know this value, I just need to find electric field here, since I know this value, and I'm gonna multiply them together to find my electric force. Okay? So I'm gonna use also Gauss's law, which is the electric flux is equal to surface integral E times dA, which is equal to the charge enclosed, Q enclosed, over the constant epsilon naught, right? That's another formula we need to know. Usually we use it when we want to find the electric field. Okay, so this is electric flux formula, or Gauss's law. All right, so for my infinite sheet right here, infinite sheet charge, they gave us a hint to use Gauss's law, so I'll take advantage of that, that the floor is an infinite sheet, essentially. And I will draw my my cube here, which will be my Gaussian surface. Oops. Okay. Don't think this will be the best cube, but will be good enough. All right, so that's going to be my Gaussian surface. And my Gaussian surface, of course, is going to have normal vectors, which I'll use. I guess I'll use this color. So my normal vectors will point up on the top face. This is a normal vector, okay? It will point, oh, that's my normal vector. Then the bottom face, it will point down, right? And then on the sides, it will point this way. And then going this way. And then on the back face, it will point out that way. And here on the left face, it's gonna point that way, right? So I have these normal vectors for each of my 6 faces in my cube, which is my Gaussian surface, okay? So if I look at that from a side view, right, then the infinite sheet will be this flat sheet from the side view. And because the infinite sheet has a -2 microcoulomb charge, so that means that the electric field is going to be pointing towards it because it's attracted to the negative charge. It will go towards the negative charge, right? So these vectors, that's my electric field vectors. In the top and also in the bottom, right? Okay. Looking at it from the side view, obviously the only faces in my cube that will be parallel to the electric field. So the faces whose normal vectors are going to be parallel to the electric field is going to be my top face right there. So I'm going to have those guys will be, oops, maybe I should use different color. So that my normal vector for my top face will be facing up, right? So that's going to be parallel. What about the faces on the side? This side, it will be parallel with the electric field, right? Or sorry, it will be perpendicular, 90 degrees with the electric field. So I'm going to ignore the area for this. I'm not going to use it here, okay? Because remember when the electric field is a constant if your normal vector is parallel to the electric field, such as the case for the top face and also the bottom face, right? Because the bottom face, actually, the normal vector is also going to be parallel with the electric field, okay? However, for these 4 faces on the side, like this face, and this face, and that face, right? Their normal vectors will be perpendicular to our electric field. And when the normal vector is perpendicular to the electric field, the electric field is equal to 0. So we're not going to mind that, okay? So we're only going to be concerned with the top face electric field and the bottom face electric field, okay? So again, I'm going to use this formula for electric flux, the Gauss's law, to solve for my electric field. Then I will plug it in here, since I know my point charge, and I will find electric force. Okay, so Gauss's law, electric flux is equal to the surface integral of electric field times dA, which is equal to the charge enclosed over the constant epsilon naught, right? Okay, since our normal vector and our electric field will be parallel, that means that electric field is going to be constant here, okay? At least for this top face and this bottom face, which is all I'm going to be concerned about. Okay, so I'm going to go ahead and take out the electric field since it's a constant. And then I just need to find the surface integral of dA for the top face and bottom face, because they're the only ones whose normal vectors are parallel with my electric field, right? All other four faces, it's going to be, their normal vectors are perpendicular to my electric field. Okay? And that's going to equal to Q enclosed over epsilon naught. Nice. So, again, the surface integral of dA will just be the area, right? The area for my two faces, which is this top face and this bottom face, okay? And the area for those, let's say my length of each side for my cube, we'll call it, what's a random letter? I guess let's call it S, okay? That's a side S. So for a cube, or sorry, for this face right here, the top face, it'll be S squared, correct? So that will be E times S squared. But remember, we have the top face and the bottom face. So we'll just multiply S squared, which is the surface area for this face, one face of this cube. We'll multiply that by 2. Okay? I'm going to also write this in black ink. So E is equal to 2S squared. Okay, and that is just the surface area of top and bottom face. Yeah, and that will be equal to my Q enclosed over epsilon naught. Okay, so now let's find out what is my Q enclosed. Recall that the surface charge density, okay, that's surface charge density, is equal to a charge divided by an area, okay? That's a surface charge density for my enclosed infinite sheet. Or sorry, that's a surface charge density for this guy. Right? And so that's going to be equal to surface charge density. The total charge is Q naught, right? That's a total charge of this kitchen floor, divided by the area of the kitchen floor, right? Which is, we'll call it, which is 4 meters times 3 meters, right? That's the area of the kitchen floor. Okay? So Now that I know my surface charge density, I'm gonna try to find my Q enclosed. Okay. So my Q enclosed, now this is for my Q enclosed, meaning the charge that is enclosed here in this. Imagine this floor. Just imagine this floor continued all the way here, right? It's an infinite sheet. So I'm looking for. Let's say this was my side view of my cube. I just want the charge enclosed right here. Okay. So in order to do that, I'm going to multiply, I'm going to multiply the surface charge density of this entire kitchen floor. I'm going to multiply that by the area right here, this area that I am going to encompass with my Gaussian surface of the kitchen floor. So that'll just be equal to s squared, right? Like this surface right here of the kitchen floor that I'm going to encompass by my Gaussian surface is just going to be, the area of that is just s squared, since my side for my cube is s, right? So that face is s squared. All right, and then I'm going to plug in this value for my surface charge density. So that's equal to Q naught over 4 meters times 3 meters, which is the area of the total floor, right? So total charge of floor divided by total area of floor. Multiply that by the side of my cube, s squared. Okay? So that is my Q enclosed. And I'm going to plug this value in to here. So E times 2s squared is equal to Q naught s squared over 4 meters times 3 meters times epsilon naught, right? The epsilon naught comes from here. So to find my electric field, that's going to be Q naught s squared divided by 2s squared times 4 meters times 3 meters times epsilon naught. Okay. I'm going to cancel out s squared with s squared. So then I will be left with Q naught divided by 2 times 4 meters times 3 meters times epsilon naught is equal to E, right? And I'm just going to plug in my values. By the way, epsilon naught right here, that's just a constant, right? It's called the permittivity of free space. And the value for epsilon naught is equal to 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Okay, so these are things you should have in your cheat sheet, right? So I'm going to plug in my values. What is Q naught? That's given to me here in the problem. So minus 2 microcoulombs. So that's going to be equal to minus 2 times 10 to the negative 6 coulombs divided by 2 times 4 meters times 3 meters times epsilon naught, which is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Okay. And if you plug that in your calculator, you'll find that the electric field will be equal to negative 9,416.2 newtons per coulomb. Okay? So I've got my value for electric field, which is here. The problem provided us with a value for the point charge. All I need to do at this point is multiply them together and I will find the electric field, or the electric force. Okay? So that's what I'll do. So F, the force that acts on the point charge, so the force acting on Q1 is equal to the point charge times the electric field, right? Actually, that's just a magnitude, right? Or actually, yeah, I can make that the vector. So what is, that's going to be equal to, what was Q1, right? Q1 is our point charge, and E we solved for earlier, right? So Q1 is given, that's the point charge, because this Q is the value for point charge. And then this problem, Q is equal to, point charge is equal to Q1, which is negative 5 microcoulombs. So I'm going to plug that in here. Negative 5 times 10 to the negative 6 coulombs. And multiply that by the electric field, which we solved for earlier. So times negative 9,416.2 newtons per coulomb. And if you multiply that together, you'll find out that the force acting on, electric force acting on Q1, the point charge Q1, which is a distance of 10 centimeters above the middle of the kitchen floor, has a force of positive 0.047 newtons, right? So that is our final answer for part A. So it's positive, so that force is going to be going away from the floor, right? So that's F on Q1, going away from the floor. If our positive was, that's our coordinate system, right? So positive is going up. All right, so that is the answer for part A. And now let's move on to part B. When released, the point charge just floats in space, and we want to find its mass. Okay. By the way, let's call this Z, X, Y. Okay, that's our coordinate system. So now we're moving to part B. So again, part B, when released, the point charge is floating. This is just floating in space at a distance of 0.1 meters, right? And we want to find its mass. And this is our coordinate system. So let's draw a free body diagram for this point charge. And once we draw that free body diagram, we can try to solve for the mass, okay? So if this was Z, okay, and X, and we'll draw our we'll draw our point charge here. Okay, so again, this is a free body diagram, or a diagram of our forces, okay, acting on a body. So here we have Q1, right? And we've determined in part A that there's a force acting on Q1 of positive 0.047 newtons, and that's the electric force acting on it due to the electric field and the point charge, right? So I have a force going up, pointing up, and that is F on Q1, or the electric force acting on the point charge Q1. But also, I have a force going down, which is equal to the mass of this point charge, Q1, times the acceleration, or gravity, right? So knowing these two forces, I'm going to write a equation of force equilibrium. So the total forces acting on my z direction, and because it's suspended according to the problem, right, that point charge just floats in space, so it's steady, it's suspended. So there's no movement, or the force is 0 along z, and actually along x and y too, since it doesn't move. So that is equal to positive F on Q1, right, this guy, facing up towards positive z, minus mass times gravity, since that points down towards negative z. Okay? So then F on Q1 is equal to mg, right? So I'm looking for mass. I know the value of gravity, that's a constant. And I know my force on Q1. I solved for that in part A, right there. So I can solve for m, right? M, my mass of my point charge, is going to equal F on Q1, my electric force on the point charge, Q1, divided by gravity. And that's equal to, what was my force on Q1? Positive 0.047 newtons. Okay, so 0.047 newtons divided by gravity, which is 9.81 meters per second squared, right? And you might say, how can I get the unit of mass, which is kilograms, if I have newtons and meters second squared? Well, actually, that's not going to be too hard because, again, everything written in blue, I hope you guys have in your cheat sheet or know by heart, but I'll write it down here, right? So the unit newtons is equivalent to the unit kilograms times meter per second squared. Oops. Per second squared, okay? So I'm going to substitute newtons for kilogram times meter per second squared. Okay? And that's going to be equal to 0.047 kilograms times meter per second squared divided by 9.81 meters per second squared, or divided by second squared, or multiplied by second squared over 9.81 meters, okay? So meters will cancel, second squared will cancel, and I'm left with a unit of kilograms, which is what I want. So if I plug that in my calculator, 0.047 divided by 9.81, that's going to be my mass of my point charge Q1 is equal to 0.00479 kilograms. Okay? And that is my final answer for part B for the mass of the point charge.